Hey guys, so today we're going to be talking about the physiology of balance. And in order to understand the physiology of balance, we need to look at these specific structures that we see in our utricle and our saccule, and we also see in our semicircular canals. So what we're going to look at are called hair cells. Now, these are important because they are what's responsible for creating the local potentials that can release the neurotransmitter that can create those action potentials, and then those will go to our brain, and then those will be interpreted as what we're doing in regards to balance. Okay, so we need to look at what's happening to them at rest, what happens when they're stimulated, and what happens when they're inhibited. So at rest, we have potassium channels that are located on the membrane of this hair cell. Now, even at rest, we're having a potassium influx. And that's because these hair cells are surrounded by endolymph. And remember, endolymph is the opposite of what we normally think about extracellular fluids. It's going to be high, rich in potassium, and it's going to be poor in sodium. So it's the opposite of what we normally think. So that potassium is going to be allowed to enter this hair cell because of those potassium channels, and that's going to cause the cell membrane to depolarize. That creates local potentials. The hair cells cannot create action potentials. So that local potential is going to cause the release of neurotransmitter, and that neurotransmitter is going to stimulate these nerve fibers that form the vestibular nerve of the vestibular cranial nerve, vestibular cochlear cranial nerve. Okay? And why that's important that this is happening at rest is because that generates automaticity. And what that means is that there is always going to be local potentials happening, even when we're just standing still, so that we can interpret, oh, okay, I'm not moving. And that's really important. So now what happens when we're stimulated, right? We're moving in a certain direction, or we could even be moving in the opposite direction. And these are going to be stimulated because the stereocilia are pointing towards the kinocilium. And that's going to cause a depression in the hair cell membrane, and it's going to cause more potassium channels to open up. So when we have more potassium channels opening up, we're going to allow more potassium, a positively charged ion, to enter that hair cell. And that's going to cause more frequent action potentials in the vestibular nerve. Now, what about when they're inhibited? They're inhibited when the stereocilia are facing away from this kinocilium. And that's going to cause the membrane to lift up slightly. And what that's going to correspond to is the closing of potassium channels. And that's going to be important because we're not allowing as much potassium to come in, we're not having as many local potentials, which releases less neurotransmitter, and because we're having less neurotransmitter released to these nerve fibers, then we're not having as many action potentials. So let's look at that in a little more detail, having to do with the utricle and the saccule. So just to review, the utricle is responsible for lateral movement detection, and the saccule is responsible for vertical movement detection. Okay, so over here we see that we have hair cells surrounded by these support cells, and they're synapsing with these nerve fibers of the vestibular nerve. Okay, now if we look at the top of these hair cells, we see the stereocilia, and then we see the one large true kinocilium. Okay, and the stereocilium and the kinocilium are embedded in a membrane, and that's going to be called the autolytic membrane. Okay? And in the autolytic membrane, we have these autolyths, and those are calcium carbonate crystals that create inertia. And that might sound like a fancy word, but all it means is that it's going to make it resistant to change. Okay, so let's look at that. So we see that we're moving in a specific direction of motion. So say we're moving this way, with this direction of motion. This autolytic membrane is now resistant to change because of these autolyths. So we're moving this way, but this doesn't want to move, which causes these hair cells to bend. And they're going to bend the opposite way of the direction of motion because it's embedded in this autolytic membrane. So if we're moving this way, our hair cells are going to bend this way. And what we're going to see on this hair cell is it's going to be stimulated because the stereocilia are pointing towards the kinocilium. So we're going to have more potassium entering that cell. and it's going to be stimulated. We see the same thing with this hair cell. But with this hair cell, we see something different, because the stereocilia are going to be pointing away from the kinocilium, and that's going to be inhibited. So we're going to have less potassium coming in, right? And that's important because when all of the information comes together, then your body, based on previous experiences, is going to be able to tell you what's going on at that moment in time. Okay? So that is going to be how the utricle and saccule detect movement, right? It's the same in both of them. But now we need to look at the semicircular canals. And when we look at the semicircular canals, we see that there is a cupula, which is kind of like this autolytic membrane, but it doesn't have these otolith crystals in it. So how is it going to detect movement? Well, we have this cupula completely surrounded in endolymph. And when we move, the endolymph is going to move in the opposite direction that we're moving. So if we're moving in this direction, the endolymph is moving in the other direction. And that endolymph is going to hit this cupula and move the cupula. When the cupula is moved, it moves the hair cells inside of it. So same principle. We're going to have the kinocilium that's moved and the stereocilium inside the cupula that's also moved when we have the endolymph hitting the cupula. Okay? And then the same principle happens. We have these nerve fibers that are synapsing with these hair cells. And it's the exact same process that's going to happen in these hair cells. And then those are going to create local potentials, right? And then neurotransmitter to those nerve fibers. And then that'll become the vestibular nerve. That'll become the vestibular cochlear nerve. Okay? So, looking at it a little more in detail, we see that the anterior semicircular canal is going to be responsible for yes movement, right? And then the lateral canal is going to be responsible for no movement. And then the posterior canal is going to be responsible for if we're doing something like a cartwheel, right? We're moving our head like this. Okay? So that's going to be the posterior. Now, how is this all interpreted? Well, we need to look at the reflex pathway and the conscious pathway. So with the reflex pathway, we're going to see that from the vestibular apparatus, the signal is going to travel to the cerebellum, and from the cerebellum, it's going to go to the vestibular nuclei of the medulla, and we're receiving information from our vestibular apparatus, right? And then we're also receiving information from our eyes. But we're also receiving information from our proprioceptors, like our joints, right? So we're receiving information from our entire body. And based off of that, in order to keep our balance, we're going to send signals to our spinal cord to be like, hey, I need to step on my foot right now, otherwise I'm going to fall over, right? And oculomotor to coordinate our eye movement to make sure that we don't get too dizzy or we don't fall. Okay? So that's going to be our reflex pathway. As for our conscious pathway, this is what we're actually going to be thinking during this time. Oh, I'm moving to my right now. Oh, I'm moving to the left right now. You know? So this is going to come from the vestibular branch of the vestibular cochlear nerve. Then that's going to be transported to the posterior ventral nucleus of the hypothalamus. And from there, it's going to be transported to the parietal lobe. And in the parietal lobe is where we receive information from our sensory perception, right? So everything is going to be analyzed there. And that's going to be how we determine what we're actually doing. And it's not just a reflex. We can consciously think about the movement that we're going to perform. Okay? I hope this was helpful, and thank you for watching.